Welcome to the deep dive. Today we're tackling something really core to algorithms,
Yeah.
how we get computers to, well, repeat tasks efficiently.
Yeah, absolutely. It's fundamental. Understanding this helps you grasp how well your code actually performs.
And everyone wants faster code, right? So, okay, we've got some great sources here looking at the two main ways we do this, iteration and recursion.
hmm Two really key programming structures.
Our goal today is to really get under the hood, understand what they are, see how they look in languages like, Python, C++, Java.
And crucially, figure out the pros and cons and when you'd actually use each one.
Exactly. Think of this as your efficient path to getting this knowledge down cold.
We'll look at implementations, weigh the strengths, the weaknesses. By the end, you should feel pretty confident about choosing between them.
Great. So let's dive straight in with iteration. In simple terms, what is it?
Basically, iteration is a control structure. It lets you run a block of code again and again, as long as some condition is true.
Like hitting repeat until someone says stop?
Pretty much, yeah. It's a structured way to loop.
And the sources focus on for loops and while loops as the main tools here. Let's start with for loops. Why are they useful?
Well, for loops are kind of the go-to when, or can easily figure out exactly how many times you need to repeat something.
Ah, okay. Like the classic example, summing numbers from 1 up to n.
Precisely. The sources show this in Python using for I in range 1, n plus 1. And you see similar setups in C++ and Java.
Yeah, and that range function in Python. I was going to remember, it stops before the second number, hence the n plus 1.
Good point. And what's interesting there is the scaling. If n gets bigger, the loop runs proportionally more times.
Right, that's our first little hint at time complexity, isn't it? How the runtime grows with the input size.
Exactly. It's a linear relationship. The number of steps grows directly with n. Double n, roughly double the work. Linear time.
Okay, so for loops are great when the count is known. What about while loops? When do they come into play?
While loops give you more flexibility. They check a condition right at the start of each loop iteration. And as long as that condition is true, boom, it runs again. The summation example works here too, shown in Python, C++, Java again.
Looking at those examples, you definitely have to do more setup yourself, right? Like initializing a counter variable.
Yep, I1 or something similar.
And then making sure you update it inside the loop, like I plus 1, so the condition eventually becomes false.
Exactly right. You need that explicit update to avoid an infinite loop. That manual control, though, is also its strength.
How so?
Well, it makes while loops really adaptable, especially if the way you update the condition is more complex than just adding one each time.
Ah, like the other example mentioned where the update logic is maybe a bit more involved.
Yeah, the while loopy example, I think, where the variable gets updated in maybe two different ways depending on things inside the loop, that doesn't fit neatly into a standard for loop structure.
Got it. So the main difference then, for loops are cleaner when the iteration count is clear up front.
More concise.
But while loops offer more control, more flexibility over when to stop, choosing depends on the specific problem.
Absolutely. It's all about picking the right tool for the job.
Okay, and building on loops, nested loops, putting loops inside other loops.
Right. The sources show this with a double for loop. A common example is generating pairs of numbers, like ij.
We see the code for that in Python, C++ to Java. The hour loop runs, and for each run, the inner loop runs completely.
Yes. And the crucial thing to understand there is the impact on the number of operations.
It multiplies, doesn't it?
It really does. If the outer loop runs n times, and the inner one also runs n times for each of those.
You end up doing n times n operations, n squared.
Exactly. That's quadratic time complexity. And it shows how nesting loops can significantly increase the workload as your input n gets bigger. Something definitely to watch out for if you're aiming for efficiency.
Good point. Definitely something to keep in mind. Okay, I think that covers iteration pretty well. Let's switch tracks now to recursion. This one sounds a bit more mind-bending, a function calling itself.
Hey, yeah, it can feel that way at first. But that's the core idea. Recursion is a strategy where a function solves a problem, partly by calling itself to solve smaller versions of the same problem.
Okay.
It usually has two main phases. There's the calling phase, where it keeps calling itself with simpler inputs, getting closer to a really basic case it knows how to solve directly.
And the second phase.
That's the returning phase. Once it hits that basic case, the results start getting passed back up the chain of calls, combining to build the final answer.
The sources mention 3 essential parts for any recursive code. What are they?
Right, super important. First, you absolutely need a termination condition. People often call it the base case.
That's the stop signal.
Exactly. It's the condition that tells the recursion, okay, stop calling yourself, we've hit bottom, start returning a value without it. Infinite recursion. Big problem.
Like in the summation example, recur,
Yeah.
the if n can turn one part.
Perfect example. That's the base case. It stops the chain.
Okay, makes sense. What's number 2?
The recursive call itself, this is the line where the function actually calls itself. But, and this is key, it calls itself with modified parameters that move it closer to the base case.
So in recur, that's the recur one bit. It's reducing n each time.
Precisely. Each call tackles a slightly simpler problem, marching towards n equals 1.
And the third element.
The return result. Each recursive call needs to return something. That return value is then used by the function that called it. In recurn, after res equals 1 gets its result back, the current call computes n plus res and returns that value up the chain.
Okay. So if iteration is like building up from the bottom, step by step, recursion is more like breaking the problem down from the top into smaller identical pieces until you hit something trivial.
That's a great way to put it. Iteration is often bottom up, recursion is often top down, or divide and conquer, 2 different ways of thinking.
Now, something that always comes up with recursion is the call stack. Can you explain that?
Yeah, the call stack is fundamental to how recursion works under the hood. Every time any function is called, not just recursive ones, the system needs to remember where it was and what the local variables were.
Okay.
It stores this information in a block of memory called a stack frame. With recursion, because the function calls itself potentially many times before returning, you get a whole series of these stack frames piled up.
Like stacking plates. Each new call adds a plate on top.
Exactly like that. And when a call finishes, its plate is taken off the top. This has a couple of consequences.
More memory usage, I guess.
That's the big one. Each call adds a frame, so recursion generally uses more memory than iteration, which might just use a few variables that get updated.
And performance.
There's also a small time cost associated with making a function call, setting up the frame, jumping execution, etc. So lots of recursive calls can sometimes be a bit slower than a tight iterative loop doing the same job.
And the stack isn't infinitely tall, right?
Definitely not. There's a limit to the recursion depth. If you call too deep, you run out of stack space, leading to the infamous stack overflow error, a very practical limitation.
Okay. Now, the sources mention something called tail recursion. Is that a way around the memory issue?
Tail recursion. It's a special case. It happens when the recursive call is literally the very last thing the function does before it returns. Nothing happens after the call comes back.
So return recurrent 1 instead of return n plus recurred 1.
Kind of, yeah. The key is that the result of the recursive call is the final result. There's no extra work like adding n afterwards. In that specific scenario, a smart compiler can optimize it.
Wow.
It can realize it doesn't need to save the current stack frame because there's nothing left to do. It can essentially reuse the current frame for the recursive call, almost like a jump in an iterative loop. This makes it as space efficient as iteration.
The tail recurrent example seems to illustrate this, accumulating the sum in the parameter res.
Exactly. The work, the summation, happens on the way down into the calls, not on the way back up during the return phase, like in the standard recursion example.
But there's a catch, isn't there?
There is a big catch. While the concept is neat, many popular languages, including Python by default, do not perform tail recursion optimization.
Really? So even if I write perfect tail recursive code in Python, it still uses up stack space like normal recursion.
Yep. In many practical environments, you won't get that space saving. It's a language compiler feature, not a guarantee. So super important detail to know, don't rely on it unless you know your specific environment supports it.
Wow, okay. That's definitely a crucial nuance. Good to know. All right, one more recursion concept. The recursion tree. What's that about?
The recursion tree is a great way to visualize how some recursive functions execute, especially ones that call themselves multiple times within a single execution path.
Like the Fibonacci sequence example.
The Fibonacci sequence is the classic example, yeah. Defined as F1, 0, F2, 1, and then Fn, Fn1 plus Fn2 for n2.
So the function fibn calls fibn1 and fibn2.
Exactly. One call branches into 2 more calls. If you draw that out, you get a tree structure. Fib5 calls Fib4 and Fib3, Fib4 calls Fib3 and Fib2, and so on.
I see. And you can visually see how the calls spread out And also how some calculations might be repeated many times, like fib3 gets calculated multiple times in the fib5 tree.
Precisely. That branching tree structure really highlights the divide and conquer nature. You break the problem into smaller subproblems, fib n1, fib n2.
And the sources say this divide and conquer idea is pretty fundamental.
Hugely fundamental. It's the basis for tons of efficient algorithms, searching algorithms, sorting algorithms like merge sort or quicksort, operations on data structures like trees and graphs. Understanding recursion helps you understand all of those.
Okay, great. We've covered iteration and recursion in detail. Let's try and summarize the comparison. What are the main trade-offs?
Well, boiling it down, iteration uses loops, recursion uses self-calling functions, time efficiency. Generally, iteration wins slightly because there's no function call overhead for each repetition.
Memory.
Iteration usually has a fixed, often small, memory footprint. Recursion uses the call stack, so memory usage can grow with the depth of recursion, potentially significantly.
And when would you use which? What problems suit each approach?
Iteration is often natural for straightforward, linear repetitions. Simple loops are easy to write and understand. Recursion, on the other hand, really shines for problems that have a naturally recursive structure.
Like the divide and conquer stuff. Trees, graphs.
Exactly. Problems where you can define the solution in terms of solutions to smaller instances of the same problem. The recursive code can often be remarkably elegant and reflect the problem structure more directly, even if it costs a bit in performance.
The sources also mention a connection between recursion and stacks. The LIFO principle, last in, first out.
Yeah, that's a neat insight. The way the call stack works, the last function called is the first one to finish and return, is exactly how a stack data structure operates. LIFO. This isn't just a coincidence. It's why you can actually convert any recursive algorithm into an iterative one using an explicit stack data structure to mimic the call stack.
The sources show this, right? Simulating the summation recursion using a loop and a stack.
Yes, the for loop recurrent example demonstrates that. You manually push state onto your own stack and pop it off within a loop.
But is that always practical? Or easy?
Often not, especially for complex recursion. While the transformation is theoretically possible, the resulting iterative code can become much more complicated and harder to read or debug than the original recursive version. Simulating the implicit call stack manually can be tricky.
So just because you can convert recursion to iteration doesn't always mean you should.
Exactly. It's a trade-off. You need to weigh performance, memory, and critically, code clarity and maintainability. Sometimes the slightly less performant recursive solution is much easier for humans to understand.
Okay, so bringing this deep dive to a conclusion then, what's the main takeaway for listeners trying to get a solid handle on iteration and recursion?
I think the core message is that both are essential tools for handling repetition. They just represent different approaches with different strengths. Iteration is often the workhorse, efficient for simple loops. Recursion provides an elegant way to tackle problems with self-similar substructures, embodying that divide and conquer pattern.
Understanding both and their trade-offs in terms of time, memory, and complexity is key to writing effective algorithms.
Absolutely. You need both in your toolkit.
So maybe a final thought for everyone listening. As you encounter problems needing repetition, don't just jump to the first solution that comes to mind, or even just the one that seems fastest on paper. Really consider which approach, iteration, or recursion will make the code easier for you or someone else to read, understand, and maintain 6 months down the line. Sometimes that clarity is the most valuable efficiency of all.
Well said. Food for thought.
Thanks for exploring iteration and recursion with us today.